Hello, welcome to the third mini lecture for this week, 10C, and we're talking about decoupling this time. We've looked at MIMOs, we've looked at the trivial case where there's no interaction between the different inputs and outputs, where it simply becomes parallel single input, single output systems. And then when there are interactions, we've looked at the relative gain array so that we can identify sometimes that there are significant pairs that we can use without further complication, and there are pairs that we should avoid. So if you can go that route, then that's best. If you can't do that, if your relative gain array has values in of 0.4, 0.5, 0.6, and there are no obvious good candidates for pairs to make a control loop on, then we need to do decoupling. Decoupling because obviously coupling is the problem, which is causing the interactions between the inputs and outputs that we don't want. So decoupling means doing something to the process to get rid of that interaction. Okay, so non-interacting control and decouplers. Here we've got two input, two output system. F1 and F2 are our inputs, and Y1 and Y2 are the outputs. And we've written down the equations that we know already in terms of 2. So let's assume pairings F1, Y1, F2, Y2. Now, as trouble is, for example, as F2 changes, both Y1 and Y2 change. And we don't want that to happen. How much does changing F2 affect Y1? Well, here's Y1 equation. So it's affected by F2 by this amount. So decoupling means we're going to do something to the inputs to try and preempt that problem and make the output of Y1 only equal to the G11 F1. So to do that, we need to adapt the input F1 to account for the input F2. So for example, if we could adjust F1 by minus G12 over G11 F2, that's how much F1 needs to change to account for this bit of interaction. So if we can adjust F1 based on what's happening to F2 by this amount, then that would cancel out the interaction, the coupling between the two. So that's the principle of the decoupler. So this is how you'd implement that. We have the control loops between Y1 and F1, Y2, F2. And what we're saying is, well, to stop Y1 being affected by a change in F2, we need to take the value of F2, put it through the decoupler, and we know the transfer function needed for that decoupler, and then add that on to our input so that Y1 has now been modified to account for the interaction between the two. So that's the decoupler. It introduces interactions between the manipulated variables to cancel the interactions between the manipulated variables and the outputs. You can do that one way, and if the coupling is two-way, of course, you can build your coupler to your decouplers to go both ways, and then it would go like that. And it perhaps it seems a bit too good to be true. Obviously, if you can use the relative gain array and just connect suitable outputs to suitable inputs for your control loops, then that's going to be simpler and cheaper and less complex, fewer things to go wrong. So if you can do that, that's the preferred approach. But if you can't do that, then the decouplers can be added in. It's another cost, another thing to go wrong, another thing to design, another layer of complexity. But it gives this opportunity to decouple. In a way, it sounds too good to be true. So let's just consider them. Decouplers require good modeling information. So a decoupler is essentially, it's a bit like a feed-forward control. In that we're using the change in a manipulated variable or the change in a variable into the system to predict a change, to predict an adjustment in order to control the output to be what we want it to be. So it's all well and good saying, oh, it needs to be this transfer function, but that's only as good as the characterization of our system, and the system characterization is always approximate. It's going to have been linearized and simplified. So it's never going to be the perfect case that we make it look like there. In practice, decouplers are adaptive. They might need to change conditions and so on at different states. The decoupling, it may be based on steady state or dynamic elements. So we were looking at the steady state relative gain array. That was how we chose the pairs for control loops. But if you're building a decoupler, you could design it based on dynamic elements as well. The other problem that you might face, the other thing that might be too good to be true, is that the design of a decoupler for the complete elimination of interactions, it might not be possible. And we'll just look at an example in a moment where that's true. Okay, so we take this example. So here we are given the transfer functions G11, G12, G21, G22, which define the interactions. And we have seen how we can design a decoupler by taking the ratio here of minus the ratio of G21 over G22. So G21 is this term here, and we're going to divide that by G22, which is this term here. So we have 2 times s plus 1 divided by 0.5 s plus 1 times 1 multiplied by e to the minus s. That's fine, so that's e to the minus s is a delay term, that's okay. That's a plausible controller to build. But if we look at the other decoupler, then we have this term, then we have this term divided by this term. So we have e to the minus 0.5 s divided by e to the minus 1.5 s, and that gives us an e to the s term. So if it's e to the minus s, that's fine, that's a delay, but e to the s tells us we're needing to know what the future value is going to be, and that's not going to be possible. So this is an unrealistic term. If you're trying to build this controller, then you would need to know future values of the variables, which of course we don't know. So this is a controller that we couldn't build. There's no way to build that, and so we can have to cope a different way. And so we can build something that does an approximate job. So we can just take the delay out. So we could build the controller with this transfer function, or simply we could build it with -2, and then it would be approximately what we want. And then you'd have to do more analysis or testing to make sure, or to assess how well that works. Okay, so that wraps up this week on MIMOs. We've just gone into a little bit of investigation to give us some general strategies for how we'd cope with it. Most of the lecture course that we've done has focused on single input, single output systems and all the detailed ways that we can build controllers for those. Of course, most systems we deal with are MIMOs, and so we've seen 3 ways that we can approach them. One, perhaps you can treat the MIMO as a series of parallel single input, single output systems. That's when your G12s and so on are equal to 0. Secondly, perhaps you can find the best interacting inputs and outputs and just build your control loops around those by using the relative gain array. But if there aren't obvious pairs to use, then we have the option of building decouplers into the system, and that will then enable us to build our control loops as we want to, without the coupled problem. Thank you very much, and good luck with your exams.